All right. Welcome, everybody, to another episode of Question Field. I am Brian. I'm joined, as always, by...
Campbell, that's me, and one other guest. Very exciting. So without further ado, why don't we just jump into the introduction? So I'd like to introduce Maria Violaris. Maria and I know each other through the student contributing members of Physics World, which is like an online publication that we both write for every now and again in our spare time. Yeah, so this is how we met, and I'm aware of Maria's other science communication work, which I find very intriguing and interesting. So this is why I wanted to get her on. But could we hand the floor over to you, maybe, Maria, and you could perhaps just tell us a little bit about yourself?
Yeah, thanks for the intro, and thanks for inviting me onto the podcast.
No, thank you.
Thank you for coming.
So an intro into, I guess, what I'm doing in general is that I'm a PhD student doing research into the foundations of quantum physics at Oxford. And yeah, my research is very much on the kind of fundamental aspects of quantum physics, partly looking at things like why we have a direction of time going in one direction, partly looking at things like quantum paradoxes and working out how everything actually makes sense despite some aspects of quantum physics looking paradoxical. So I think of that.
Just the simple things.
Yeah. Yeah, I see it as
Good
like
stuff.
paradox busting of a...
Is it paradox? Do you sort of take a paradox and say, "Oh, don't worry, the world still works," or do you come up with paradoxes?
Yeah, it's kind of a mix. Yeah, I like to look at a paradox and work out why everything's okay and why we don't need to worry about it. But sometimes along the way, I'll end up coming up with a thought experiment to test a particular idea, and then investigate something using that thought experiment. But yeah, I think for most things, quantum physics makes a lot of sense once you look at everything properly.
Yeah. Oh, fantastic. So, I mean, it sounds like a fascinating research area. And you also, of course, do a lot of work in sort of science communication as well. Are you able to sort of explain a little bit about what you've had experience in that field?
Yeah. I've always really enjoyed science communication, giving talks and presentations and things. So then I started, I made a video about quantum computing during an internship I did with Riverlane, which was kind of like quantum education focused. And I made this Raspberry Pi quantum computing lab and then made a video about it, and then kind of carried on making videos after that with IBM Quantum for the KissKit YouTube channel. And the idea of those videos, it's an ongoing video series where I've made 5 so far on that playlist. I've got 9 more coming up.
Oh, wow.
Wow.
That's very exciting.
Yeah, essentially doing paradox busting by taking a quantum paradox and then explaining what the thought experiment is and how to make sense of it using the ideas behind quantum computing. And yeah, that's pretty fun making those videos.
Fantastic.
And we will have everything in the show notes. So, Maria, whatever you want to send us that you'd like for us to share, please hit us up with that and we will get it out there.
Absolutely. Yeah, so I guess the idea for this podcast, usually we sort of base the podcasts around a question, potentially one that somebody has written in. So I guess the question for today, I don't know, do you have an idea, Brian, what we're going to call this episode? It could be something like, why does quantum mechanics actually make sense despite all apparent reasons to the contrary?
Campbell has a really fun time of trying to see how many words we can fit onto my little Chiron when I make our social media posts. Yeah, let's go with that one.
We can end up with hundreds of words of essay with a question mark at the end.
The font is just going to get smaller and smaller.
Yeah, so we were hoping to speak to you, Maria, about quantum paradoxes, and the whole area of quantum mechanics obviously is sort of rife with paradoxes because, well, quote unquote paradoxes, right? Because I guess it sort of arises whenever you try and use your classical intuition to try and understand something which is inherently non-classical. So, I mean, is there a good starting point that we could jump into? So, if like your run-of-the-mill paradox that could reveal something about quantum mechanics?
Yeah, probably the best starting point is the most famous quantum paradox that so many people have heard of that it's kind of become a meme in popular culture, which is Schrödinger's cat, of the cat being dead and alive at the same time. And that's often said to be a paradox because one way of saying it is that it seems like Schrödinger's cat can be dead and alive at the same time, but in everyday life we never see cats being dead and alive, and that's the idea of the paradox.
Mm-hmm.
So yeah, I could give a kind of summary of what the paradox is in case a listener has not come across it.
Sure, that'd be great.
Sure, please. Thank you.
The kind of original setting of it is that we imagine having a cat in a box, and it's trapped in there with a radioactive atom which may or may not decay. And if it decays, then it will release a small hammer to smash open a vial of poison, and that will kill the cat inside the box. But if the atom doesn't decay, then the cat will stay alive because the poison will never be smashed open. And the quantum twist is that, according to quantum mechanics, the radioactive atom can be in a superposition of being decayed and not decayed, meaning that it's somehow decayed and not decayed at the same time. And if you treat everything in the box using quantum mechanics, so you say, oh, I can describe my hammer using quantum mechanics, I can describe my vial of poison using quantum mechanics, and I can describe my cat using quantum mechanics, then if everything in the box is described by quantum mechanics, what you end up saying is that if the atom decayed and didn't decay at the same time, then the hammer did and did not smash the poison open, the poison did and did not kill the cat, so the cat is both dead and alive inside the box. But we know that every time we actually see cats, they're dead or alive, and we never see anything be in this weird dead and alive state. And that is what Schrödinger was trying to show, the absurdity of applying quantum mechanics to large objects like cats, because it seems to lead to this phenomenon that we don't see in everyday life when dealing with objects like cats.
Ironically, the sort of dissemination of this idea, the memification of Schrödinger's cat, has made it much less absurd because we're all much more used to this concept of a cat that's dead and alive now. So what's your take on it then? Do you feel like that we just have to accept that the world is quantum and that, there can be superpositions of dead and alive cats? Or do you think that there's, some question mark surrounding, where quantum mechanics maybe breaks down or turns into classical physics?
Yeah, my take on it is that I don't think the idea of a cat being dead and alive at the same time is a paradox in itself because of the fact it's absurd. I think the paradox is, why do we never see cats being dead and alive at the same time? And that's the bit that needs explaining or resolving to make this not a paradox anymore.
Mm-hmm.
I think we have good explanations for why we don't see cats being dead and alive at the same time, which is the fact that, so often in explanations of quantum mechanics, people will say when an observer looks at the cat, it collapses into being either dead or alive, and that this is a kind of fundamental property of quantum mechanics, is this collapse of things from superpositions into just one state when an observer looks at it, and people kind of say that looking at it is really important somehow.
Mm-hmm.
I think this kind of seems really weird, like why would an observer be so important? And what actually resolves the paradox is not that observation causing collapse is this fundamental quantum extra rule in quantum mechanics, but it's actually that if anything from outside the box kind of interacts with the cat, then it will join in this superposition of the atom and the hammer and the poison and the cat. Once that happens, then the cat kind of behaves as though it's dead or alive, rather than behaving as though it's both at once. So when you can also apply this to the observer, because once an observer opens the box, they join into that superposition and there's a version of the observer seeing the cat dead and a version of the observer seeing the cat alive. But it's actually not even special to an observer, just a single particle interacting with the cat in that box would also join in that superposition and have the same effect. So, some people don't like this idea of there being multiple copies of you seeing the cat dead and alive, but it's at least doesn't have the paradoxicalness of seeing. It has a way of explaining why we never see cats dead and alive at the same time.
Sure. Yeah, so this is kind of like a many worlds interpretation kind of answer to the paradox, I guess. Is that would you say that's fair?
Yeah, that's right. So the many worlds interpretation says that if we treat observers as being quantum mechanical, then they'll behave in this way where one of them will see a dead cat, one version of you will see an alive cat if you've looked inside the box, and these multiple copies of you are kind of like multiple worlds. Although this explanation in general of treating the environment around the box as being described by quantum mechanics isn't specifically... There are other theories as well as many worlds that are consistent with this idea, and a more general way of dividing the kind of explanations for Schrödinger's cat is the ones that say that there's a collapse, so that the cat becomes kind of irreversibly fixed into being dead or alive. And then there's the ones that say there's no collapse, meaning that the cat ultimately stays being dead and alive simultaneously, even though if it doesn't look that way to the observer. And many worlds is one of those no collapse theories, and something like the Copenhagen interpretation, which says that an observer looking at a cat causes an irreversible collapse, that would be in the collapse batch of theories.
Yeah, it sort of retains some of its flavor of a paradox in that it makes all of us kind of confront our assumptions about quantum mechanics a little bit. It's like it kind of, for somebody who believes in a collapse type of interpretation, so something like the Copenhagen interpretation, where a measurement or an observation sort of causes the particle to be located here and only here, for example, as opposed to somewhere else. It sort of makes you confront this question of, okay, well, when does that collapse occur, and why does it occur, and that kind of thing. So or on the other hand, if you're a fan of decoherence ideas and sort of removing the collapse from the theory, then it sort of forces you to swallow the fact that yes, you have these very crazy sounding ideas that are true according to your interpretation of the theory.
Yeah, I mean, I think that in a way the Copenhagen interpretation, I mean, my personal view is that it shouldn't actually count as an interpretation, because it doesn't actually tell you like when this collapse is supposed to happen. So it doesn't, there's no definitive answer of whether the hammer can be in a superposition of having smashed the poison and not smashed it, and whether the poison can be in that superposition, and whether the cat can be in that superposition, whether an observer
Right,
can.
exactly, yeah.
And so I think thinking about this problem, which, is kind of known as the measurement problem of quantum mechanics, I think when you think about it deeply enough, you become forced to kind of abandon the Copenhagen interpretation and say, okay, if I'm going to think about collapse, I need to pick a specific theory which tells me how that collapse happens. And that's when you get things like objective collapse theories, which give you specific conditions of when that collapse would happen, which you can then use to determine whether or not your theory says that you're allowed to put hammers in superpositions, and then you can experimentally test whether you physically can put these larger and larger objects in superpositions to test those theories, basically.
Yeah, which are sort of like not quite interpretations as well either, are they? Because they sort of add something on top of quantum mechanics that isn't already there. Yeah,
I think they're different theories rather than interpretations, but the word interpretation has kind of stuck to thinking about these ideas for historical reasons, in a way.
Yeah, I guess just to defend Copenhagen a little bit, I guess it comes at the whole wave function thing from a little bit of a different point of view, right? It tends to be a little bit more epistemic in its philosophy, I think. Thinking of the wave function as describing something about our state of knowledge and what we can know about the system, as opposed to what is sort of objectively characterizing the system. So it's sort of like, well, where does the collapse happen? Where do you want it to happen? I mean, it's like you can sort of draw the line anywhere, because it's sort of about the accuracy with which we can know certain things, I think. I mean, maybe that's not a fair characterization.
Yeah, I think that's the type of approach in like cubism, where it's kind of, it kind of says that you can have like knowledge of a quantum state, or that the quantum state is not a fundamental physical entity, and it's more about retrieving information about it is what is central to where collapse appears to happen. But I guess that there's this whole philosophical issue of whether you're a realist or a non-realist, and the realists would say we want theories. Our theories should describe physical reality, and that's what makes them good theories. They're like our best guesses at what physical reality is. And if you're a non-realist or using that philosophy, then that might say that we can't guess at what physical reality actually is, and we can just, improve our predictions of how well we can predict things, for example.
Right.
Yeah, I think I'd probably fall into the realist camp.
Yeah. I mean, I guess I think I remember reading Feynman. I could be getting this wrong. I think Feynman said something along the lines of, like, in response to this question of instrumentalism versus realism. Instrumentalism being, just something along the lines of, and I'm not a philosopher, so I'm probably going to bungle this, but something along the lines of the value, like the worth of a scientific theory is not about how well it describes some sort of objective reality. We don't have access to that. All it's good for is sort of how well it performs in providing predictions and how useful it is in some sense. And he says, well, yeah, but nobody does science from an instrumentalist motivation. Nobody says, oh, well, I'm going to study this because it's going to allow me to predict things with 10% better accuracy. That would be absurd and like horrendously depressing. So people do science because they believe that it has some bearing on objective reality and allows us to understand something about the world. Well, so now that we've warmed up a little bit with Schrödinger's cat and gotten nicely sidetracked in philosophy, should we jump into a different paradox?
Yeah. Well, there's a thought experiment. It's not so much a paradox as a thought experiment related to what we were just talking about. Well, we mentioned this idea of are these different interpretations or are these different theories of quantum mechanics? And historically, it might have seemed like these were different philosophical interpretations of whether there's this irreversible collapse or whether there isn't, and that it all leads to the same predictions. And so it's a philosophical question, not a scientific question. But what I think is really cool is that there's a thought experiment that David Deutsch came up with in an attempt to give a way of testing between the many worlds interpretation and Copenhagen interpretation, in the sense of testing between observation causing an irreversible collapse and causing no collapse at all. And essentially what this thought experiment rests on, just explaining it in my words, is that you imagine an observer measuring some quantum system that's in this superposition of two states. Let's say they have a quantum coin which can be in a superposition of heads and tails at the same time. Then the observer looks at the coin and observes whether it's heads or tails. They see a single outcome. And we imagine that we are an experimenter that has control over this observer. So yeah, we could imagine that you, Campbell, are in a lab flipping this quantum coin and measuring it, and then I've got access to some controls over this lab and you and the coin.
Sounds like a terrifying proposition.
I was going to say.
Very intense. Then all you have in this room is you have a pen and paper, and you write down, once you've measured your coin, you don't write down whether you got heads or tails, but you write down, I definitely made a measurement, or I, Campbell, definitely made a measurement, and you sign it so that we know that that's you and it's your handwriting and everything, and you have this evidence on this piece of paper that you definitely made that measurement. And then you can imagine, like, you slip that paper under the door, and I then have that piece of evidence that you made the measurement from outside the lab. And then what I do as the controller of the experiment is I attempt to reverse your measurement of the quantum system, so of this quantum coin. And because I have full quantum control over the lab containing you and the coin. And then what happens is, if your observation did not cause the coin to irreversibly collapse, if everything was reversible, then I can successfully reverse you and the coin. And I like to imagine that the coin began like spinning clockwise, and then you measured it and saw heads or tails. And then if the reversing happens successfully, then the coin will be back to spinning clockwise. And then I can check at the end of the experiment whether the coin returned to spinning clockwise. And if it did, then I successfully reversed the measurement and everything. And that's evidence for no collapse having happened. But if you observing the coin actually irreversibly put it into either heads or tails, then what would happen is that half the time the coin would go back to clockwise, half the time it would go back to anti-clockwise, to the direction it's spinning. And then if I then check whether it's clockwise or anti-clockwise, and I repeat this lots of times, then half the time I'll get one outcome, half the time the other. And that way I can deduce that there was an irreversible collapse when you did your measurement. And so, armed with these results, if I get the same outcome each time of clockwise, then you can come out of this lab, you won't remember anything about what you measured because you've been completely reversed. But I can show you this piece of paper giving you evidence that you definitely made a measurement, and I can show you the results showing that it was reversible. I managed to reverse it. Even though your memory was erased, you still have this evidence of having made a measurement. And so this is a way of experimentally testing whether or not you actually cause a collapse or not.
That sounds very intriguing. So, wow, interesting. So I guess just for some added context, quantum mechanics has these two, well, in the sort of generally kind of accepted and taught formulation of quantum mechanics, there are sort of these two modes, right? When you're not looking at things, everything evolves reversibly, and nice and smoothly, and what we call unitarily. And when you do look, when you do make a measurement, then that's when you get this irreversibility. So this is why this reversibility is very important in the thought experiment. Okay, interesting. What are your takes on it? Do you think that this is do you see any issue with this thought experiment, or are you sold?
Yeah, I think the thought experiment itself is really good for being a way of distinguishing these, the idea of irreversible collapse and collapse. So, it was thought of as a way of distinguishing many worlds and Copenhagen interpretation, but more broadly, it's, distinguishes the collapse and no collapse. And I think the kind of question that comes up from this thought experiment is, well, what counts as my observer, or what does it take to actually, what would I have to do to actually do this experiment? And then the kind of most extreme version is that you'd have to, if I actually wanted to have full quantum control over Campbell, then probably the best way of doing it would be to come up with a theory of consciousness or something and create a simulation of you, and then have you running on a computer, and then so that's where the idea of a quantum computer, even though it wasn't called that at this stage, was kind of proposed through this thought experiment, because Deutsch was trying to suggest ways of how you would actually implement it. Would be, maybe we could use superconductors as logical equivalents of physical systems and do some kind of simulation which has to be able to behave quantum mechanically to do this, to simulate this measurement and reversing it. But that would require a kind of fully fledged way of simulating an observer, which we can't do until we have a good theory of conscious people or simulating people. But we can definitely do a lot of things on the way to that. Like, we can have the observer being something of a certain mass, for example, to test ideas of gravitational collapse against no collapse theories. And we could have the observer being something of a certain complexity to test an idea that a certain level of complexity causes collapse. Or we could push the boundary up to the kind of smallest possible living system to test if something being living causes collapse or not. And so, basically what the observer is in this thought experiment depends on what the collapse theory is that you're testing against, and you have to make it meet the requirements of the thing that's supposed to cause this collapse to happen.
I see. So something that I find somewhat confusing about this thought experiment is when I write down when I write down whether or not I've made the measurement and I pass that slip of paper through the door, that seems as though you're extracting some information out of the room, which is kind of what a measurement is, right? Even though you're not measuring the coin itself.
Yeah, that's a good question. So the kind of key insight here is that the thing you write on the piece of paper reveals that you definitely made a measurement, but it doesn't reveal any information about the measurement outcome that you got. So it doesn't reveal anything about whether you got heads or tails. If it did reveal even the slightest bit of information about whether you got heads or tails, then this reversal, me trying to reverse the lab, reversing your measurement, wouldn't work, because I would still have a bit of that information outside the lab, and that would have essentially caused this effective apparent collapse, because that's the kind of source of decoherence, is a little bit of information leaking out of the controlled environment and not being able to take that into account anymore. So what happens in this case is that I do measure the fact that you made a measurement, and I store my evidence of that, but it doesn't interfere with reversing you doing the measurement. So I don't actually reverse everything, because if I reversed everything, then I would also reverse you writing on this piece of paper that you got this measurement. So I don't reverse the bit of you recording that you got a single outcome. But yeah, even with that piece of evidence, I can still reverse the important bit for getting the coin back to the superstition it started off in, with the heads and tails at the same time.
Yeah, interesting. Yeah, so it's if there was any, like, if the result of my measurement influenced how I wrote down, yes, I made a measurement at all, then that wouldn't be possible. Sort of like this leaking of information outside of the lab. Yeah,
that's right. So if it turned out that you seeing heads made you feel happy, and you feeling happy means that your handwriting is better or something, then that could actually cause some issues for this experiment. So probably a better way of doing it would be that, like, there's a button you push for heads and a button you push for tails, and it'll print out some generic thing that's not dependent on your not sensitive to slight changes in your actions.
Yeah, interesting. Do you know of proposals for performing a very simplified version of this experiment, for example, in a quantum computer? Like if we take our internal observer within the lab to be like a qubit or something along those lines, is that possible, or is that too simplified?
Yeah, I mean, I think we can already do a kind of qubit version of this thought experiment, and it kind of has been done, I think, with with small numbers of qubits, in the sense of putting something in superposition. Yeah, I think kind of simulations of this where the observer is a qubit have been done. And I guess the idea of my IBM video, the Qiskit video, is that, well, the idea of all the videos is that I turn the thought experiments into quantum circuits, which are a way of explaining how we run it on a quantum computer. And this particular thought experiment just needs a few qubits. I think it's 3 something, and not that many operations done on them, and it becomes quite simple to do on a quantum computer, which you can do on a simulator or on a cloud device that you can access. So people could do simulations of this at home if they feel so inclined. But I think probably the soonest one that would actually test this for a meaningful collapse theory will be with masses testing gravitational collapse.
Right.
Yeah, because I think everyone is convinced that qubits can be in superposition, and them kind of decohering in a very simplified way can be reversed if you've got control over everything.
Yeah, exactly. We're not going to be sort of confirming or denying many worlds with 5 qubits, but yeah. Well, it would be very exciting if some sort of gravitational interaction and decoherence process was able to be reversed.
Mm-hmm.
Cool. Okay. Yeah. Well, what's another interesting one that you've maybe talked about elsewhere?
Yeah, I can tell you about one of my favorite ones. I think one of the reasons I like this one so much is that, like, it feels kind of underrated that not that many people know about it, given how interesting of a thought experiment it is, which is the quantum bomb tester.
Fantastic. Is this going to involve me in a lab again, but am I going to be blown up this time?
Yeah, that's a good idea. Let's have you as the experimenter again. Dealing with the bombs. Yeah, so you can imagine that I give you a box which may or may not have a bomb inside. And this potential bomb is sensitive to a single photon. So if a single photon or any single particle of anything interacts with it, then it will explode. And your challenge is to work out whether or not there is a bomb in the box without the bomb exploding.
Certainly seems impossible.
Yeah, so if in your lab you only have classical equipment or you only have knowledge of classical physics, then unfortunately there is no way for you to figure out whether there's a bomb in the box without it exploding, because even if, like, you could imagine trying to bounce something, throwing something into the box and seeing if it bounces off or not. But even if you do that with a single photon and see if the photon comes back to you or not, then it would trigger this bomb to explode if it was there. So there's absolutely no way of working out if it's there without it exploding, if it is there.
That's right, I didn't need to know anyway. Not that fast. But there's clearly a quantum method that does a bit better.
Yeah, so the cool thing is that there is a quantum method of doing a lot better, which is that all you need is a photon and a beam splitter, which is it's like a half-silvered mirror. So if you send a photon, a single particle of light, through a beam splitter, then it will split into an equal superposition of being reflected and going straight through. So it goes into this state of being in these two pathways at the same time of being reflected and transmitted through the beam splitter. So you're actually going to need two of those and two mirrors and two detectors as well. And then what you do is kind of hard to explain without a diagram, but
the perennial challenge of this podcast.
Yeah. Yeah, I've never had to explain this audio only, but have a go.
We can always put some diagrams in the description if if you want to refer to something that is not currently available for the listener. They can always find it down below.
Cool. Well, I will refer to my quantum bomb tester video, which has some cute animations of this.
There you go. Very, very good plug.
Yeah. I'll imagine that Campbell's in this lab and I've got like a voiceover trying to explain to you how to check whether this bomb is in the box. So yeah, what you have to do is you have a source of single photons, you send a photon through a beam splitter, and then what you do is you put your box, which may have the bomb or not, into one pathway of the beam splitter. So where the photon has split into these two pathways, you put the box in the way of one of the pathways, and then let's imagine that the box has little holes in it. So if the bomb is not there, then a photon would pass straight through this box because nothing would be blocking it. And if it passes straight through, then basically you use the mirrors to divert these pathways of these two pathways of the photon back together, and then you make them meet at a second beam splitter. And when they meet, they'll merge and they'll just become like one beam again because of interference, like the same kind of interference you get with water waves, like constructive interference between these two pathways of the photon. And then you'll get, you put your detectors at the end after this second beam splitter, and then you'll always detect that the beam has come out at the same place because it's just merged, the photon's merged back into a single photon. So that's what happens if there's no bomb in your box. But if there is a bomb in your box, then there'll be a 50% chance. So essentially, the bomb will detect your photon, and that will cause it to be projected into one of these two pathways because of this apparent collapse that happens. And either there's a 50% chance that the bomb will explode, and unfortunately that's game over. Or there's a 50% chance that the photon ends up in the other pathway, not the one with the bomb. And then when it reaches the beam splitter, the second beam splitter, it actually splits 50-50 into two parts again because it doesn't have another part to interfere with. And then it will be detected half the time at one detector and half the time at the other because it's been split 50-50. And so if you ever detect the photon at the detector that it wouldn't go in if it had merged back with itself, then you know for sure that the bomb was in your box without having set off your bomb. So that's the exciting outcome. It's the one where you've managed to work out that there is a bomb in the box with absolutely nothing interacting with your bomb, which seems like a paradox.
It certainly does. So it's this, if we use the language of measurement for now, although that might be insulting to many worlders. So it's this sort of measurement that has collapsed the location of the photon to the other arm of the beam, which doesn't include this bomb-containing box. It's sort of this like, it seems like there's no interaction, but it was sort of like in one branch of the wave function that was where the interaction occurred, and the interaction sort of produced this measurement, which then collapsed the state of the photon to now only be going in this like right hand arm, for example, of the beam. Super interesting. Yeah. Do you think it reveals something about quantum mechanics?
Yeah, I think it's it's really strange, and like it's very paradoxical there's some ambiguity about the word paradoxical of whether you use it when something is like literally inconsistent or whether something just seems really weird.
Yeah.
I think this definitely seems really weird, like the idea that you can work out something is there with nothing interacting with it. And it's really strange how, you can kind of use this to, for example, one of the suggested applications of this is that you could use it to image delicate objects, for example, because you can work out that they're there without anything interacting with them. And it's really weird that you can do that. And what's quite cool about this paper is that, so it was proposed by Elitzur and Weidmann, two physicists, and Weidmann, I think it was coming from Weidmann that there was a suggestion in the paper that this was that this really is paradoxical, the idea of detecting the bomb with absolutely nothing interacting with it, and that actually this thought experiment is evidence for a many worlds interpretation, because there must be, if you're in a world where the photon hasn't interacted with the bomb, then there must be another branch in the universe where the photon did interact with the bomb or was absorbed by it and caused it to explode, and that has to have physically happened somewhere in the universe in order to explain how you're able to get any information about the bomb without having interacted with it, because it would have exploded if a single photon interacted with it. So like whether or not you find that convincing, I find it very cool that that this thought experiment can provoke such a kind of intense conclusion, in that this may be like a genuine paradox with collapse theories by some arguments.
Yeah, I think that, to me, that argument suggesting that this is a paradox seems to kind of, as we warned before, it seems to rely a little too much on classical reasoning. You know, you can either send a photon to interact with the bomb, or you can't, right? Whereas it's like we wouldn't be particularly surprised if we just, like, you know, sent this photon off on a beam splitter and put the bomb in the way of one of those parts and not in the way of the other one. You know, we would say, well, there's like this 50-50 chance. But I guess it's, to me, it seems like, well, there's no paradox, right? Because it's just that's the way that quantum mechanics works. And if we try and use our classical intuition again, then we run into problems. But I don't know. it is fascinating.
Yeah, I think the essence of the strangeness is that, I guess the question posed is like, if I have this object and I've somehow retrieved information about it, but I haven't affected that object at all, then that's the kind of the root of what seems paradoxical. Like, how could you retrieve information about it with absolutely no effect on it? But I see what you're saying, that it seems like, okay, well, that's just what quantum mechanics says.
Yeah, no, but it does still feel, as you're saying, it does feel paradoxical. Yeah. It's just difficult to know to what extent we should trust our intuitions when it comes to these like paradoxes. Yeah,
I mean, this idea of the interaction-free, so it's kind of known as interaction-free measurement, and it leads to some strange things when applied to other. It's been kind of extended to this. For example, there's counterfactual quantum communication, where the idea is that, let's say we have like Campbell and Brian are trying to communicate using a... the idea is that you might be able to communicate just by having the possibility of sending a photon from Campbell to Brian, but not actually having to physically send it, by using a similar idea of like, somehow it can be arranged that you never actually need to send that photon physically through, as long as there's the potential for sending it.
School children everywhere trying to avoid their homework just perked up.
There's the possibility that you can do your homework that's just as good as already doing it. Yeah.
This is one of those topics where there's like paper after paper responding to each other on different sides of this topic, because one paper will be out saying like, this isn't real counterfactual communication because there's some little trace of the photon somewhere, and then the next paper will come out saying, actually, there's no trace of the photon, and then they'll kind of argue about what counts as having a small trace of the photon, and whether it's really this bomb tester style thing going on. So it's all a bit messy, but ultimately the idea is that if this is fully possible, then you might be able to like send a message with nothing, no one eavesdropping on your message, because if there's no photon for them to capture, then they can't hear what you're saying or intercept what you're saying. So I think it's a conceptually cool idea, but I'm not well versed on the details.
There seems to be something that maybe links this with the previous thought experiment, which maybe I am going to misrepresent one or both of them by trying to draw this link. But in the bomb tester case, there's this sort of there's this superposition, right? And in one branch of the wave function, a measurement occurs, whereas in the other one, no measurement occurs. And the sort of result of that in some way is that you can somehow sort of perform a measurement without having to actually perform the measurement. And in the other one, it's like we've got this quantum object, which is the observer in the lab, along with their quantum coin, and the quantum object sort of performs a measurement and then gets some information back without communicating that to the outside world. So it's sort of like this it feels like this kind of boundary between measurements being fully classical and destroying the quantum nature of the system, and measurements being just another quantum interaction where we can think of one particle sort of measuring, quote unquote, another particle by just sort of interacting with each other, but they still are describable with quantum mechanics. It's sort of this like strange middle ground between these two extremes. I'm trying to suggest that there's like they both kind of play in this middle ground between measurements being reverting the quantum system to a classical system, and measurements just being another quantum interaction between constituents.
Yeah, I think that this point is at the core of like almost every quantum paradox that we tend to think of, or the kind of well-known thought experiments that are around in quantum mechanics. And I kind of had that realization as I was yeah, like I said, I have 9 paradox videos upcoming, and I made 5, and I just kind of realized as I was writing all these scripts, like, I'm literally doing the same thing in every video, which is saying, like, they're all in very different contexts, all kinds of different situations, but ultimately almost every one of them comes down to saying, look, if we treat the measurement device as a quantum system and treat the measurement as a quantum interaction, then everything's fine. And this happens in lots of different contexts, like the Schrodinger's cat example, this observer in the lab, the bomb tester. It happens there's one called Wheeler's delayed choice quantum eraser, has a similar solution. The double slit experiment is also well known, that has a similar solution. Entanglement, quantum teleportation. Yeah, most of them have this idea at their core, but kind of in very different contexts. But yeah, when you ultimately abstract everything else away about what the story of the thought experiment is, and just look at what's actually happening to, let's say, the qubits that you're using to model the thought experiment, it's always kind of resolved by treating this measurement as a quantum interaction between quantum systems. So yeah, it's kind of fun. Like the last video is on quantum time loops, which are kind of like
cool.
The technical term is closed time-like curves. So yeah, essentially contemplating whether if time travel is consistent with quantum mechanics and what happens when you have loops in time with quantum mechanics. And I quite like that one because it actually it goes beyond this whole like everything's fine if we turn measurements into quantum interactions, because then when we try and think about time loops, we actually need to think about like new physics beyond standard quantum mechanics, and actually things become like genuinely beyond the kind of standard quantum mechanics, whereas the other things are kind of like, actually standard quantum mechanics is fine. But yeah, the measurement thing is definitely the underlying core of a lot of apparent paradoxes.
Yeah, super interesting. This is something that that has, I guess, bothered me a little bit with many worlds, I guess, is that, to explain my thinking, the sort of closed time-like curves and this kind of bringing in extra physics reminded me of the gravity discussions that we were having before. And this is, I guess, maybe where it seems to me that many worlds kind of goes a little bit beyond an interpretation and into a theory, just like the objective collapse theories go beyond interpretations. Because if we sort of take it seriously that there is no collapse, that all quantum systems remain sort of in some branch of a large global wave function, then you sort of have to take it seriously that gravity is also quantum and can form superpositions just as well as anything else, right? And then that really goes beyond anything that is proven, right? That's like an extra assumption on top of what we currently have reason to believe.
Yeah, so that is a good point, and yeah, it is related to a cool thought experiment, which is not one that has appeared in my videos because it's I don't know how you seem. Well, yeah, there's a thought experiment to test for non-classical features of gravity that my supervisors proposed, Vladka and Kiara, which is to. Yeah, it's essentially based on this idea that if gravity has quantum features, then if you put a mass in a superposition of 2 different locations, then gravity should then be in a superposition of those 2 different locations as well, because the mass will have a force of gravity in those 2 different locations. And you can essentially do the thought experiment here. The gist of what you do is that you imagine that let's say you isolate 2 masses so that the only way that they could interact is through gravity, and you essentially check if you start off with those masses not being quantum entangled, and then you let them interact, the only way they can interact being gravity, and then you check if they have become entangled. And if they've become entangled, then the only way they could have interacted was by gravity. And from that, you can argue that you can prove that gravity must have some non-classical features in order to enable that entanglement to be generated between the two masses. So that's a really cool thought experiment for testing between these kind of proposals for gravity between the non-classical gravity ones and the classical gravity.
Yeah, so I mean, maybe at some point in the near to medium future, we might be able to test these claims.
Yeah, there's lots of people trying to work on kind of scoping out what these experiments would take to physically implement them, which would be really cool.
Yeah, Maria, this is a hopefully not as loaded question, but given the content you create and given what you study and work on, I feel like we're also, generally speaking, culturally, there's never been more like mass media that has dealt with quantum realms and multi-worlds. And I'm wondering, like, does that make your job as a communicator easier in the sense that everybody has some kind of fundamental notion, or does the fact that there's this fundamental notion out there make your job that much harder because you maybe need to break that notion down? I'm just kind of curious how you tackle that, or if it's even something that you wrestle with or contend with when you're writing a script or something.
Yeah, it's an interesting question. I think, it's kind of useful that Schrödinger's cat has kind of come into the popular consciousness, because I like to use it as a way of kind of introducing what I'm going to say, because I could be like, have you heard of Schrödinger's cat? Like, that's what I'm working on. Like, I describe it as like more complicated versions of Schrödinger's cat, and then I can expand into as much detail as that person is interested to hear about. So that's kind of useful as a starting point, because I feel like starting with like, did you know that things can be in two places at once can be like really strange for someone who's not heard of that notion at all.
And also quite boring for you to have to explain every time.
I don't know. It's kind of, on the flip side, it's kind of fun explaining things like the bomb tester that most people have not heard of, because you kind of get to start with a clean slate in a way and build up to the interesting ideas without, I guess, dealing with preconceived ideas about what's happening.
Right.
But I think every person, I guess, has very different background, a different level of knowledge about it. I guess I have some general things which it feels like everyone thinks about them a certain way, and I kind of wish that we had more popular science explaining them a different way, because it feels like a slightly flawed idea has entered the popular consciousness. I think that there's two of these that come to mind. One of them, which has come up in this conversation, is the idea of the Copenhagen interpretation being like a kind of, I think it's often thought of as the sensible interpretation or explanation of quantum mechanics. And when you actually look into it, like, people disagree about what the Copenhagen interpretation actually is, and then you have to go more specific than that, and then people are much less comfortable defending specific versions of it than, I don't know, I feel like sometimes it's used to kind of say like, everything's fine, like Copenhagen interpretation, that's the sensible thing, right? But then it's not actually, it's not actually a worked out interpretation, it's more an umbrella word. And the other thing is, which hasn't come up in this video, but is maybe a story for another time, is the spookiness of entanglement, being that if two quantum objects are entangled, then doing something to one of them has some kind of instant influence on the other one, and that's a very that's an idea throughout like popular explanations of quantum mechanics and amongst scientists as well. And for a long time, I didn't know that there was actually an explanation of quantum mechanics without any of this instant action between one part of the universe and the other. And when I found that out, I was like, oh, like, why doesn't everyone know about this? Yeah, so those are the two things that I would like to shift the popular view on, if I could.
When you're watching a TV show or a movie and these ideas come up, are you able to kind of flip a switch and just enjoy stuff, or you're just always going with this?
Yeah, I think if it's fictional, then I'm completely fine with that. Like if the word quantum is being thrown around in some fictional thing, then it doesn't offend me if the science isn't right, because I mean, I don't really have a particular view that the science should be all right in a fictional thing. Although, sometimes I wish that maybe some of the more interesting aspects. So, like, for example, a lot of popular fictional media might use the word quantum or talk about quantum and kind of use it as a way of either maybe talking about a really fast computer that just does the same things that a classical computer does, but it's like super fast or something, and they'll say it's quantum, or they'll use it as a way of having like many worlds in the story. But I kind of feel like the idea of many worlds isn't it's not like the characteristic thing of quantum mechanics, because you can also get that from lots of theories of cosmology. There are lots of theories of many worlds, and there are kind of ways that many worlds... people have been thinking about the idea of many worlds for a very long time, long before quantum mechanics, and I kind of feel like if you're going to draw on quantum mechanics as inspiration for fiction, there are probably cooler things you can do with it.
Sounds like a challenge. You're challenging the creative community.
That's a very good point.
Yeah, there's a few creative quantum competitions out there, like the quantum shorts that CQT in Singapore run. I think it alternates between a story and a video based on quantum fiction. I think, people get creative with quantum things in those, which is fun.
That sounds very cool. Brian, your question made me remember watching Avengers Endgame in cinemas a few years ago, because I was just thinking, well, it can actually, being familiar with some commonly used terms can make, popular media even more entertaining, because in that movie they say something like, I think they throw around the word EPR paradox at one point, which is, that's a thing. Don't know what it has to do with time travel, but and then at some point they say, oh, we have to work out the eigenvalue of the Mobius strip, which is the most hilarious combination of words I've ever heard. It's like, what does that mean? Just some funny, some mathsy sounding words they throw in. Anyway, but sorry to derail. Yeah, well, thank you very much for joining, Maria.
Yes, thank you so much.
I'm very much looking forward to seeing those 9 extra Paradox videos. I'll be keeping a keen eye out for those.
Oh, yeah, thanks for the fun discussion.
Yeah. Cool. Well, we will, I'll hand over to Brian to wrap it up.
Well, yeah, thank you, everybody, once again for listening. As always, thank you, everybody that has reviewed. Thank you, everybody that has left a star rating on your podcast app. Recently, we got an email that Campbell is among the top 20 physicists,
physics podcasts
in Australia, podcasting physicists. Yeah.
Thank you so much.
So congratulations, Campbell. Let's get him in the top 10, everybody. Maria, anytime you want to come back and just give the world a piece of your mind on the direction of time or any other thought experiments that come your way, we are your stage. So thank you very much. You're welcome back anytime. Campbell, thank you as always, and especially for shouldering a lot of this one. Although I was piqued by the idea of being the sole host with this quantum bomb test, but so in some other worlds, it's all mine. But in this one, Campbell remains my co-host. So thank you. We will catch you next time, everybody, here on Question Field.
You've been listening to Question Field. Question Field is a Gain Media production and is produced by its hosts Campbell McLaughlin and Brian Buchanan. For more information, please check us out on Instagram at QuestionFieldPod, on Twitter at QuestFieldPod, and on TikTok at QuestionField. If you have a question you'd like to submit, or would simply like to leave a message, please send us an email at questionfieldpod@gmail.com. Recently, the James Webb Telescope discovered 5 new stars located in the review section of your favorite podcast app. Thank you for listening.